morning, everyone. My name is Rahul, and I'm an engineer on the Android Toolkit team.
And hi, I'm Tomáš, and I'm engineer on the developer relations team. And today we're going to talk about how to make apps blazing fast with baseline profiles.
So far, we've announced baseline profiles early this year, and we have about 250,000 apps publishing with baseline profiles on the Play Store. This was even before some of the toolchain for building and publishing with baseline profiles was ready. Now that everything's ready, I'm going to make a claim. You can probably make your app at least 30% faster if you use baseline profiles. The reason why we are so confident will become clear once you understand how code execution evolved in the Android platform. We look at execution in 3 dimensions. First is initial performance. This is performance after an install or after a process cold start. Second is eventual app performance. This is performance after the runtime has a chance to discover some hot paths in your code, for example. And third, we'll look at the cost of these optimizations in terms of additional disk space required. In Android 1, your code was interpreted. So the runtime initial performance was slow. Eventual performance was also slow, but importantly, we didn't use any additional disk space. This is because we didn't really do much to optimize your code. There's nothing to save. This was a key consideration back then because disk size in early devices was really hard to come by. In Android 2, we introduced a just-in-time compiler. This additionally, so even though your code started off in interpreted mode, the just-in-time compiler would discover hot paths and optimize them. But those optimizations got thrown away once the process died. This is, again, a key consideration because disk space was paramount. In Android 5, we decided to do something slightly different. We introduced full AOT, or ahead-of-time compilation. The way this worked was, after app install, we ran a new compiler called dex to oat. And this converted your dex code to optimized dex file. So we compiled it at install time. And once the user interacted with the app, they only loaded the odex files, which is the compiled code. And as a result, the user saw the performance improvements. Now, 2 caveats here. First, we introduced a new compiler, dex to oat. Remember, this is running on a resource-constrained device. So this is not particularly fast. Also, we are optimizing the entire app. Second, there's the cost of storing that compiled code. This also gave us this dialogue. Anyone remember this? The reason why this happened was every time we introduced a new optimization, we had to compile every single app on the device to take advantage of those optimizations. So this was clearly not ideal. Going back, we improved some performance characteristics though. So we made app launch faster because we have a new compiler. We made disk size a bit worse because now we have the cost of storing that compiled code. So in Android 7, we decided to do something that took advantage of the best of both worlds. So we wanted to not compile the entire APK because that was slow. And we wanted to identify the important parts of the app. So to do that, we went back to a hybrid between just-in-time and compiling the important parts of the code. We called it profile-guided optimization. And the way this worked was you start off the app in interpreted mode with the just-in-time compiler like you saw before. But instead of throwing those results away, we would store them additionally in a file called profile. A profile is just a list of classes and methods that are important for us to convert to machine code to make sure the app is fast. Once the device was idle, that compiler that you saw before ran in something we call background dexopt. So we would only target the methods and classes in the profile, and now we would only conditionally compile them instead of compiling the entire app. This was much faster because we knew exactly what parts of the app are important. And when the user was interacting with the app the second time, we have the odex files and dex files, and given we've optimized the important parts of the app, the user sees the benefits in performance. And not only that, this process repeats again and again. So as the just-in-time compiler discovers new hot paths, it can dump them into the profile that can be picked up by subsequent passes of background dexopt, which is great. So let's look at the table now. So we've improved disk size usage because now we're no longer compiling the entire app, but now we have a mix of slow starts and fast starts. right? We have slow starts because your code starts off in interpreted mode with the just-in-time compiler, like before, and then eventually gets fast. So if you were to plot app startup time and days since install, you would see something like this. As the just-in-time compiler knows more, it optimizes more, app launch typically gets better. It's not just that. This story repeats on every single user device, right? It's more like this. So every time your app is installed on a new device, we start from scratch. But wouldn't it be nice to take advantage of profiles that are computed on devices that were similar to yours but not your device? So trying to crowdsource this profile information. That's exactly what cloud profiles are. So in Android 9, we introduced cloud profiles. The idea is to identify common traits in profiles on a device that were generated on a device similar to yours and on a platform version similar to yours. And we start aggregating them, right? So we identify those common traits, and we upload that aggregated profile to Google Play. Once we have enough of those profiles, that profile is then provided to the app at install time as APK metadata. And then new users will see the benefits, and they'll see a much flatter curve. This is because we took advantage of profiles from other devices, and then we used it on new devices, right? So this is great. One caveat, though, the profile aggregation can take several weeks, because it really depends on how often your app is used and how many users you have, for example. So the more users your app, the more passes we have at background desktop, then we can build a better profile. Let's revisit that curve. So now, if you look at performance characteristics, we have a new caveat here, which is every time you release a new version, we don't have profiles. And so we have to start over again. This happens every single time, right? Every new version. So if you've seen something like this before, we're sorry, but now you know why. Okay, now let's go back to the table. We've improved on initial performance because now we have cloud profiles from other devices supplanting profile information generated on your device. So let's look at the curve again. This is the curve as it stands today during Android 9. What we really want is this. We want app startup to be fast in the beginning, and we want it to remain fast. That's where baseline profiles come in. Baseline profiles are a way for the app to provide what is important to the runtime. So it's a way for you to bundle that information into the APK itself, and we consume that at publish time and app launch time. It's not just for apps, though. It's also for libraries. So when a library like Jetpack Compose declares baseline profiles, all consumers reap the benefits, and they can take advantage of it. And finally, I want to stress that the toolchain is now stable. So if you've seen problems before, you won't run into them anymore, I promise. And it should be a much better experience. Baseline profiles can be backported all the way to Android 7 because we can take advantage of some of the same toolchain, Dex to Oat namely, and we can backport a lot of the same functionality all the way to Android 7. That covers approximately 95% of the device population. And so we solve the slow start problem because you're telling us what to optimize ahead of time, and then we give you great performance to boot. And if you include Android 5, which does full AOT, that means profiles are used in 99% of the device population. So that was a lot of theory, and now I'll hand it off to Tomáš, who can show you how to generate them.
Thank you. Okay, to get started with baseline profiles, you can use Jetpack Macro Benchmark library to generate them. You write a simple instrumentation test, let's call it baseline profile generator, in which we'll use a baseline profile rule that will provide us all the necessary scaffolding. And we write a test method, generate, in which we use collect baseline profile method from the rule. It requires two parameters. First, the package name of the app you want to generate the profile for, and second, the profile block lambda, in which you write interactions of your app. As part of the interactions, you should cover your most important user journeys of your app, such as app startup, scrolling the feed, adding stuff to the basket if you're an e-commerce app, and stuff like that. But also, You may cover journeys that are not called as often, but are worth optimizing. This could be a user login flow, sign-up flow, etc. That's because these journeys may not be covered with Cloud Profiles soon. But also, if you've got some kind of A/B testing in your application, you may consider covering both of the scenarios, because the slower performance of one of the scenario actually can affect the metrics of the A/B testing. All right, let's write some interactions for the Now in Android sample app. We'll start with start activity and wait. This will start the default activity of your application and actually waits until the first frame is rendered. Once the code of your app is executed, the library takes care of capturing all the called methods and classes in the background. Next, we wait until the content is asynchronously loaded and ready and shown on screen. And again, once the test is executed, the code will be collected again. In our example, scrolling the feed will be one of the most used features. So we find the feed on screen, and we scroll it with the flick gesture. Again, triggered code will be collected in the background. So once the test is done, all the reference methods and classes are saved on the device in a text file. The file looks something like this. There's no magic there, just some classes, methods in a human-readable form. You can read it, but you definitely don't want to write it yourself. So that's why we recommend generating it with Macro Benchmark library. And this file basically is the baseline profile. So next, you just need to copy the file into /main folder next to the Android manifest and name it baseline.prof.txt. And that's it. Next time, later, when you build the production version of your app, if any dependency you use has a profile, it will be merged with the one you just generated and included into app APK or app bundle in a compressed binary form so that it doesn't take a lot of space. And then you can just upload it to the Google Play, where it's processed for various device versions. Once uploaded, it can be distributed to your users in two ways. The first and most optimized way is when you install your application on Android devices running 9 and through Google Play. That's where the cloud profiles also can be distributed. So in this case, when your users install the app for the first time or they update it from the previous version, it will download the APK and also the processed baseline profile. And on device, the package installer installs the APK and it uses the included profile to run a targeted DEX optimization at install time. And that means that the optimized DEX files are generated even before the app is launched. And users see the performance benefits from the first start of your app. But also on Android 7, that's 7 and between 9, the package installer doesn't know how to install the rules. So we've got a fallback for that. And not only those versions, but also like if you don't ship your app through Google Play on other services, that will work as well. The only thing you need to do is add Android X profile installer dependency to your app. So in this case, when users download the APK with baseline profiles, the package installer installs the app, but it doesn't optimize it immediately. So when user opens the app after the install or after the update, it runs in interpreted and just-in-time mode, as before. But also, the profile installer knows where the current profile, where the profile is, and what format it needs. And so we save the included baseline profile rules there, similarly as the just-in-time compiler would over time. And later, when the device becomes idle, the rules from the profile are compiled, and we'll get the optimized text file based on the baseline profile rules. So next time the user opens the app, it'll be optimized and run fast. This means you should always add the profile installer to your dependencies. Now, let's see how to verify the benefits of baseline profiles. There are two ways. The first option is you can check your field metrics. That is Google Play Vitals, Firebase Performance Monitoring, or any other service you use for metrics of your app. You should see improvements of your app startup or smooth experience, but that's only after you ship the version of your app. To check it in the lab environment, like on a CI or locally on a device, we can use the same Jetpack macro benchmark library. So again, we write an instrumentation test, and we use this time macro benchmark rule from the library. This will provide scaffolding for benchmarks. And in this case, we write a helper function, startup, that we'll use in our tests later. It'll use measure repeated method from the rule. We need to fill in all the necessary parameters, that is how many iterations, what package to start, and what metrics you care for in the benchmark. So we care for the startup timing metric. But then we'll also write one optional parameter of the method, which is compilation mode. This will help us distinguish between when the app uses a baseline profile and when not. And last thing, we write a measure block lambda, in which we specify the interactions with the app similarly to the baseline profile generator. So here we've got press home to start the app from the launcher always, you've got start activity and we wait until the content is loaded and ready to use. Now that we've got the helper defined, we just write two tests. One that uses compilation mode none, that runs the app in the unoptimized state without baseline profiles, and one that uses compilation mode partial, which partially precompiles the application. We should run these benchmarks on a physical device. If you can, run it on the most frequently represented device so that you see the impact for the majority of your users. The results come directly on Android Studio output pane. You get duration in milliseconds, so you get slowest, fastest, and median startup time. So in our case, what we can see is that the app started over 100 milliseconds faster with baseline profiles, which is 40% improvements. That's even bigger than Rahul said in the beginning. And the slowest run was even longer than that. The other way to look at these results, or verify if they work, is with system tracing. Macro benchmark records system tracing of every iteration of the benchmark, and it provides the traces within the same within the same output pane. So you can just click on the first iteration of the compilation mode none, and it will take you directly to the system tracing profiler. So let's do it. So here, we've got the compilation mode not, and we can see that in the system tracing profiler, there you could see a lot of information. But what we want is we'll search for the JIT thread pool. That's the bottom pane. We can see that during the startup, there was a lot of work executing, and that is the just-in-time compiler compiling the interpreted code. So that's the thing that is doing. If we open the other test, the trace from the other test, from the compilation mode partial, we would see that in the JIT thread pool, there's almost nothing happening there. And that's because the code is already compiled before the app startup. And that's the massive performance boost you can get. You may see that there's still some tiny speck here that can happen sometimes. But with system tracing, you can investigate more, and you can improve the profile generator so that next time it covers actually it. Now, performance is not just about numbers and metrics and profiling. It's actually about the actual user experience. On the right side, we see that with baseline profiles, the app starts faster. But it's not just about app startup. It's actually about smooth experience as well. So the app scrolls smoother, animations run smoother. So the performance gets better in any case. And bear in mind that we didn't have to rewrite the app. We didn't have to change the architecture of our app. We just had to write an instrumentation test and follow a simple process. Your new users will get better first impression of your app, and existing users will get consistent performance. There are some links you can follow for more information. We're here later to answer all the questions. Now go and make a baseline profile. Thank you.